Welcome again to Introduction to Fluid Mechanics. We are in Chapter 3, which deals with writing the conservation equations in integral form. That is, writing the conservation equations of mass, momentum, and energy for a controlled volume. So far we have dealt with mass conservation for a controlled volume, and we're moving on to discuss how the linear momentum conservation equation is written for a controlled volume or in integral form. So first thing, what you will see here is that linear momentum conservation for a fixed mass is written as so: the rate of change of mass, the rate of change of linear momentum, which is mass times velocity, for a fixed system, fixed mass system, is equal to the summation of all the external forces. So that's Newton's second law. Summation of forces is equal to mass times acceleration. And what Reynolds transport theorem helps us do is rewrite this equation for a non-fixed mass system, but rather a system with masses, mass fluxes coming in and out of the controlled volume. So this is what it looks like for a controlled volume with fluxes of mass coming in and out. So the summation of forces is equal, the summation of external forces acting on the controlled volume are balanced by the rate of change of the time rate of change of linear momentum inside the controlled volume, plus the fluxes of momentum in and out of the controlled volume. So this is our starting point right over here, and let's look at the terms that that are involved in this formulation. So we have a controlled volume, and in that controlled volume, masses could be coming in, and as these masses come in, they carry fluxes of momentum with them. So they carry momentum just because the mass has a velocity, and velocity is associated, the velocity of a mass is associated with momentum. In its most simplistic form, the summation of force that was for a fixed mass, the summation of forces would be equal to mass times acceleration. This is what we are familiar with. And the first thing we want to note here is that this is actually a vector equation. So this is not one equation, it's three equations in one for each Cartesian, one for each of the three Cartesian coordinates, or whatever coordinate system you're using. So the forces are the external forces acting on the controlled volume, and here you want to pay attention to two velocities that we refer to. One is the absolute velocity, so that's the velocity observed by someone sitting on a fixed ground. So this is the absolute velocity that contributes to the momentum. So if you look here, density times volume gives you a mass. Mass times velocity is momentum. So this is the rate of change of momentum inside the controlled volume. So that's what this term right here is. So that's the rate of change of all the momentum, that's what the integral is, of the entirety of the momentum that's included inside the controlled volume. Why do we have the integral sign in front instead of writing it as such? Because you can imagine that inside the controlled volume, parts of the fluid, now we're talking inside the controlled volume, parts of the fluid can be moving at a different velocity than in other parts of the controlled volume. So we have to include all these effects and sum them up through this integration. So that's the first part. So this is that is linear momentum accumulation or loss inside the controlled volume. If this term is positive, then it's net accumulation of momentum, and if it's negative, then it's a net loss of linear momentum in the controlled volume. Now on the right hand side, the second term is actually the fluxes of momentum that come in and out of the control volume. And we started by saying you want to pay attention to that we have two velocities. One is the absolute velocity, that's the velocity observed by someone sitting on the ground, and we have here a relative velocity that we have seen when we were talking about mass conservation, and this is the velocity of the fluid seen by someone sitting at the boundary of the control volume, that particular boundary. So that's the relative velocity that gives us the mass flow rate. So density, density times V relative dot NdA, that's actually mass flow rate, so that's m dot. And if you want to be more accurate, it's dm dot. And this is the velocity that contributes to the linear momentum, which is the absolute velocity observed by someone sitting on a fixed ground. So you'll see the velocities contributing to momentum in either of those two terms on the right hand side are actually the absolute velocities. So you want to pay attention to that. And again, why do we use an integral? That happens when the velocity there is velocity variation over the surface of the control volume. So at the boundary of the control volume, you might have a non-uniform velocity coming into the control volume, and that's associated with a variation in momentum that we have to sum them all up bit by bit through this integral. So these are the fluxes of momentum coming in or leaving the control volume. And lastly, the summation of forces, we leave it to the last term to discuss. It is the external forces acting on the control volume. And again, I want to remind you that this is a vectorial equation that has three components. So this is actually three algebraic equations in one. So what may constitute an external force acting on a control volume like the one that we have here? One is pressure force. So that is when you're cutting through a fluid, just like we have done when we were dealing with a static fluid. You expose a fluid, and the fluid and when you expose the interfluid forces, or the force between a fluid and a surface, that most definitely is going to involve a pressure force. So that's your pressure force. And now that we don't have a static fluid, but rather we have a moving fluid, we can also expose the viscous shear fluids. That's the frictional forces that exist between fluid elements themselves, or between a fluid element and a solid object. And then we will have body forces such as the gravitational pull. The gravitational field of the Earth contributes on a mass, so mass times gravity, so that's a gravity force. You can also have other body forces like magnetic forces and electric forces that will be part of those body forces. So in cases where fluids like metallic fluids, they can be subjected to electric fields and be affected by electric fields and magnetic fields, then you would probably need to include those forces into your body forces along with the gravity. Surface tension, we haven't dealt with it in this course, so we are just going to skip over it. And then the last thing is, if your control volume is cutting through a solid object like a bolt or a weld, like we have done in the past, or a pin or so, then you have to include the effect of that exposure of the solid material by its contributing forces, by the internal forces that you have exposed by that cut. Okay, so now what if let's make this simple, and let's say, what if at the boundaries of my control volumes, at the control surface, the fluids coming in and out come in as one-dimensional, so they come in uniformly distributed. They don't have variation. So in that case, that integral sign will now turn into a summation sign, just because the velocity does not vary over the area. So all you need to do is just multiply the mass flow rate with the velocity, the absolute velocity. And then you're still having your unsteady term here. So the summation of external forces will be the rate of change of momentum within the control volume plus the fluxes of momentum coming, leaving the control volume minus the momentum of fluxes coming in. And if this is confusing you, why it's out minus n instead of n minus out, it all comes from the mass conservation equation. So please check that out in the previous lecture. It's because of the v dot nda, and that's how ins and outs are defined. It depends on the cosine theta. So you have this v dot nda, which is part of the mass flow rate, and this is a dot product, and depending on the, because v dot n is v times n cosine theta, depending on the cosine theta, whether it's 180 or 0, you get a minus sign. So that's the whole story. So it's summation of fluxes out minus n. And then if you have a steady problem, there isn't time variation of your velocity or your mass inside within the controlled volume, then this term cancels out, and you end up with the summation of external forces on your control volume will be balanced by the fluxes of momentum out minus in. And again, the external forces, just like we have discussed before. So let's take them one by one, and let's focus on those two, the pressure and viscous shear. Just because gravity is straightforward, it's just the weight, and we said let's skip over surface tension. And a solid force, it's also straightforward. It comes from our statics, the study of statics. When you cut through a membrane, a solid membrane or a solid object or a solid surface, you expose the internal stresses, and you need to account for those in your force balance. So what the fluidic part, which we're particularly interested in, barring the surface tension, which we're going to skip over, are the pressure forces and viscous shear friction forces. So remember, if you had a liquid, for instance a cup of water, and we had that previously in when we were talking about static fluids. If I take a control volume, or actually a control surface, so I could have this being my control volume, but I'm considering the straight line as my control surface. So by doing that, by taking this control volume, you have exposed, you've thrown away the rest of the cup, and you kept this fluid that's within the imaginary boundary that you have drawn. And for that, you now really need to include the effect of what you have thrown out on the control volume that you have. So the fluid that's right over here is imposing a pressure force, or is exhibiting a pressure force that acts compressive and perpendicular on this particular surface. That pressure could be varying, or it could be uniform, or it could be hydrostatic, or it could be hydrodynamic. That means it varies with, it doesn't vary just hydrostatically. So it could be any of those, but we need to include the effect of the fluid that we have thrown away on our control volume. And similarly, you do the same thing for the rest of your control volume. So that was for a static fluid, because the definition of a static fluid is that it does not sustain any shear forces. But now that we might have, let's say in this cup you have a spoon, and you're mixing the fluid inside, you're stirring it, so you're creating a motion. And on this controlled volume, now you have, so let's draw this control volume again. You might have shear shear stresses, which will act parallel to the area that you are that you have exposed. And similarly, you will have shear stresses on other parts that act parallel to the area that you that is under effect. And what is this shear stress that we have drawn here, this tau? This is shear stress, and here we've drawn the pressure. It is the friction that the part that we have cut away and thrown away, which is outside the control volume, it is that effect, that friction, that mass is acting on the mass inside my control volume, or on the boundary of my control volume, whether it's shear, that is shear force, parallel force to the area, or normal stress, which is the pressure perpendicular to the area. So that's what these are. So that's when you're cutting through a fluid. So that's the fluidic effect. So if you look at the pressure force, the pressure acts compressive, so it acts towards the area, and here the N is the unit vector pointing away from the control volume. That's why the minus sign tells you it's a compressive. So the pressure force will be pressure times the area, and those two signify the direction. So it signifies that it's compressive. The minus sign signifies that it's compressive towards the surface. So that's the pressure force. And let's take a case where the pressure is uniform, so it comes outside of the control of the integral. So you end up with the N times dA. And if you take this is a control volume, and the pink line is the control surface, or the boundaries of my control volume. And the N vector, as we said previously, always points away. It's a unit vector pointing away from my control volume, outward from my control volume. And when you sum those unit vectors all around this closed control surface, that integral is actually going to come to 0, because the pressure is now outside the control, outside the integral. But in cases where, but this is not always the case, you can have a uniform pressure, such as the atmospheric pressure acting on your control volume, and now we have shown or seen that the effect of the atmospheric pressure, or any type of uniform pressure on our control volume in its entirety as a net, is actually going to be equal to 0. But often the pressure is not uniformly distributed. You might have a uniform component, which is the atmospheric pressure. On top of that, you will have non-uniform components, which you have to actually integrate, and you have to not only integrate as algebraic, but also you need to take care of the directionality, which was what we have done in chapter 2 when we dealt with static fluids. We looked at the horizontal and vertical components of that pressure force, and if you are in 3D, you want to consider the 3 components of that pressure force. But again, the basic principle is that pressure is compressive, that's hence the minus sign, and it's perpendicular to the area, with N being the unit vector pointing outwards from the control volume. And in a very similar fashion, the shear stress, we can compute the force due to shear stress. Shear stress times the area gives you the shear stress force, just like the pressure times the area gives you the pressure force, except shear stress acts parallel to the area, and while pressure acts perpendicular to the area. So you want to keep that in mind. One thing also to keep in mind is that why would shear come into existence? It comes into existence because there is rubbing between fluid elements, and that happens when you have a faster fluid moving closer to a slower fluid. And in this case, that's what we call a velocity gradient. And when you have a velocity gradient, then if you look at this fluid element and this fluid element, they're rubbing shoulder against each other. So that's going past this one, and it's rubbing shoulders, and that's creating friction between them, and similarly between this fluid element and the one beneath, and that's the shear stress. And where would you expect this friction between those two elements to be pointing? It'll be pointing in the parallel to the velocity. So if u is the velocity vector, or let's call it just v, so the velocity vector, as you can see, is going to the right. Definitely you're going to expect that your shear stress is actually going to be a friction. So, and friction is going to impede your motion. So your shear stress is going to oppose your direction of motion. But your velocity and the shear stress are parallel to each other, although with a 180-degree angle between them. So they're parallel to each other. Shear stress and velocity. So in a case where so that's the shear stress, and in case that there is no gradient so let's take another case. Let's take the case where let's take the same case. The velocity is acting in this fashion, and that's the only component of velocity that exists. Because shear is parallel to the velocity, I would not have in this case shear that is in the y direction, just because all the velocity is in the x direction. So in this case there is no shear, while in this case the shear is parallel to the velocity. So keep that in mind. This is something. This is a new concept that we haven't considered in the past. So take a moment to just let that sink in. That shear stress is parallel to the direction of motion, as you've been familiar with in your dynamics course and other courses. Very well. So now I think we can do a quick example. And here what you have is two pipes, pipe number 1 connected to pipe number 2 and they're of different diameters. Pipe number 1 is 8 centimeters, pipe number 2 is 5 centimeters. They are connected to each other through a flange. So maybe this is a new concept to you. We will talk about what a flange is. And what they have is that they give you the pressure at the section number 2, and they have this measurement device, which is a manometer, which we have dealt with in the past. So if you look here, the fluid inside the manometer itself is static. So you want to keep that in mind. Again, maybe this is a it's hard to swallow at the beginning, but you want to consider that the mercury manometer is just a measurement device. It just doesn't affect any aspect of our force balance or mass balance, just because it's a passive device that's just sitting there to tell us what the pressure difference between the center line pressure of pipe 1 and the center line pressure of pipe number 2. So that's all its job is to do that. And even though it looks big on the picture, and its effect, it doesn't have any effect in terms of force and mass balance, and the fluid in it is static. However, the fluid in the pipe is actually moving, and we want to consider that. So the question is, we have those two pipes connected through a flange, so we will talk about a flange in a second, and the question is, if the pressure difference as measured by the manometer is 58 centimeters of mercury, what is the tension force in the bolts? The bolts are holding those two pieces of pipe together. If you didn't have bolts, this one will just fly away. Just like if you stick a nozzle at the end of your garden hose, if it's not securely secured in position with the appropriate fixture, it's actually going to just be ejected, and it'll just fly away. It won't be held in place. So that's what these bolts on the flange do, is they keep the two pieces together, the two pipes together. So let's talk just for a moment about flanges. So how can you attach two pipes together? The familiar method that you probably have in mind is pipe threading, which is more, you see that quite a bit in households, so you might be familiar with. And in this case, you have a male part of the thread that has a matching and mating female part, and they fit together. And this is great and works very well, but it only works for low pressures, so domestic applications and so on. And if the pressure starts going higher and higher than the standard applications, what you can have is that these threads, these teeth, are actually going to strip. They're going to break, and the two pieces will just come apart, and eventually you're going to get a leak. So if you want a mechanism or a way of connecting pipe 1 with pipe 2 that can still hold a much higher pressure, your best bet is to use a flange. And what a flange is you take looks like so. You have pipe A, which is this pipe right here. You weld a plate so you weld this plate to it, and this is the weld over here. And you drill holes, and for the second pipe you do the same thing on the other side, and then you use a bolt and a nut or a set of bolts and nuts to join the two pieces together. So the weld and the bolts are much stronger and can sustain a larger pressure and a larger load than what a thread system can support. And here's another example. So this is your pipe. You weld it to this thick flange so it can still sustain a lot of pressure, and you weld it here, as we've said. Then you have them in between the two flanges. So this is flange 1, and this is flange number 2, which is connected to pipe number 2. This is pipe number 1. So they're mating flanges, and what you do is you drill holes and you put the bolts through, and you tighten them up. To prevent leak, you would add a layer in between, so where the metals meet, the two faces of those plates meet, you would add a rubber gasket or some form of gasket to prevent leakage. So this can sustain much higher pressures, and it's for larger scale. It's hard to thread, and as well as to fit together larger diameter pipe systems. So as your pipe system starts going larger and larger, you're going to tend to see flanges to be the more prevalent method for connecting fittings and pipes together. Okay, going back to our problem. So the question is, what should the flange for the bolts that are holding the flanges together, what force will they sustain in this particular case? So here's our piping system, and this is what's given for us. And the first thing is we want to choose our control volume. And as you might have guessed, if I'm interested in the force on the flange on the bolts, I need one part of my control volume to cut through those bolts. And then I could continue. I need to close this control volume because this is what I'm after. But then I could have option A, which is go and cut through a different piece of pipe if I want to close my control volume, or I can go to the open air where I know what my pressure is. So if I do this, I have now exposed those forces, the tension forces in the pipe number 1, the larger pipe. While if I continue my control volume to the right, I am only exposing atmospheric air, which I know pretty much everything about it. So which one would you pick? Obviously, you're going to pick the control volume to the right, as we have done here. So you're going to use this control volume where you know what your pressure is. They tell us that the pressure is atmospheric, and you know what your mass flow rate and so on and so forth. And you'll see we're not really, I'm going back to the point that this mercury manometer is just a measurement device. It's not part of the system per se. It's just a passive type of equipment that just what it does, it just tells us the pressure. Okay, so you're always better off starting. So we're after the force, but it's always cheaper, and the smarter way to do it is to always start with mass conservation. Mass conservation is an algebraic equation. It's easy to write and implement. So you're at a controlled volume, you might as well just start with conserving mass, because that mass is really what's carrying the momentum. And if you don't know what mass flow rate is going through your system and its distribution through the conservation equation, then most likely your force balance is actually also going to be off. So might as well just start with mass conservation, and for this control volume. So, and let's conserve the mass of water. So we see water going through this section of the control volume, and it's leaving through the other section of the control volume. So let's see at what velocities they come in. Since the water inside the control volume does not change in time, so it's a steady type of problem. There are no indications that our flow is unsteady, because we have sort of a steady velocity of 5 meters per second. The manometer height is 58 centimeters. H is fixed, so nothing is varying with time. So it makes sense to the rate of change of mass inside the control volume is equal to 0. So that's equal to the fluxes of mass in would be equal to the fluxes of mass that leave the control volume. So that's what we've written over here. M.1 is equal to M.2, which is equal to M dot. And it is the density multiplied by velocity 1, area 1, which is equal to the density multiplied by velocity 2 and area 2. And the densities go away. The area is pi d squared, and you have diameter 1 and diameter 2. Now you get a relationship between V1 and V2 in terms of the diameters. So V1 and V2 in terms of the diameters. So V2 is just what we have seen this before in mass conservation, is the diameter ratio squared. So we have V1 of 5 meters per second. So now we get V2. So V2 is 12.8. So you see, we came in at 5 meters per second, and a reduction of only 3 centimeters from 8 centimeter to 5 centimeter has, or let's say a reduction of 3/8, so that's more like 30%, has given us more than 100% increase in velocity. So my velocity more than doubled from 5 to 12.8 due to that change in area. So the area being, in the first one it was 8 squared times pi over 4, and here it's 5 squared times pi over 4. Okay, so actually it's 8 over 5, so that's 1.6. So there's a 60% difference in the area. So you see, our mass balance has helped us find out what velocity the fluid was leaving at. So because that's the velocity which is creating the momentum, we know that the mass flow rate that comes in is the same as the mass flow rate that leaves the control volume, but this mass flow rate comes in with a low momentum because it's multiplied by a lower velocity, while it leaves with a higher linear momentum, V2, so it leaves with a higher momentum flux. And that momentum flux, as we have been talking about, that momentum flux balance has to be balanced by some external force. And what are the external forces acting on my control volume? So let's see. So that's my force balance, and let's do it in the x direction, so sigma fx, and then that will be Vx, and here we have m dot Vx out minus Vx in. So what forces are, let's start with the force balance. What forces are acting on my control volume in the x direction? So the control volume is this green control volume. So let's see. One is we are cutting through the bolts. Perfect. So we've cut through the bolt. So what we have done is we've taken the right hand side of the control volume and thrown it away. So now, because we have thrown it away, we have to replace it with its effect, and its effect is really the force of the bolts. We've also thrown the water that's here, so it contributes a pressure. So the part that we have thrown away is acting on my control volume by a pressure that is compressive and perpendicular. Similarly, here I have pressure that's compressive and perpendicular, and I'm only dealing with the forces in the x. I'm only doing a force balance in the x. So I would also have atmospheric pressure here and atmospheric pressure outside. So the liquid or the fluid that's here is water, the fluid that's here is, in this part outside the pipe, is air. So the air also contributes with a pressure that's the atmospheric pressure. Okay, so these are the forces. So we have, let's call this area, so I'm going to confuse you a little bit. This area, we're going to call it A1, and this whole area of the, so A1 is just the area of the pipe, that whole area I'm going to call it A2. So just bear with me, it just makes things, I'll just reduce one step. So the forces, we said we have the P1A1 acting on this section, and then we have A2 minus A1, which is this area right here. All that area is A2 minus A1, and we have the atmospheric pressure acting on it. So there you go. And then on this other side, we have the water pressure, which is P2 is equal to P atmospheric, as you've seen here. That's what given part of the problem is acting on the water side, on the water, that's the water pressure. It's compressive and perpendicular. And then you have the air here also contributing with the same pressure on. So over the whole area A2, I have P atmosphere acting on it. So P atmospheric times area A2. Okay, so that's the pressure force. And because the velocity is going to the right, and the shear stress acts parallel to the area, and parallel to the area, and also parallel to the velocity, I wouldn't have shear stress here because the area and velocity are perpendicular. And in this case, the area and velocity are perpendicular. When the area and velocity are parallel and I have a velocity gradient, then I will have a shear stress. So I don't have shear stress on the inlet or on the outlet. And again, we're only doing the shear stress in the x direction, so it does not exist in this case on the other boundaries. Okay, what other forces do we have? We've talked about we're still doing Fx. Then we have the force due to the bolt. Or we might have one bolt, we might have 10 bolts. So all of them, the sum of all of them, I'm going to call it F bolt. So it's not 2 times F bolt, it's just all of them, and this is just a representation of all the forces due to the bolts. So these are pretty much the 2 forces that we have. We've exposed a pressure by exposing the liquid, and we've exposed a metal force, which is the bolt force, by exposing the metal, by cutting through the metal. So we have P1 minus P atmospheric. So if you subtract the 2 pressures in the positive x direction, it'll be P1 minus P atmospheric multiplied by A1. So you see, try and work that slowly, and it's not P1A1 minus P2A2. Please the areas will because then you're going to have a missing part of the area. So please work this out more slowly than we have done here. Then you have the force of the bolt. It's acting to the left, so we're doing the forces and velocities to the right in the positive x direction to be positive. So that's why the F bolt is negative. And in case, because we've drawn it in the negative x direction, and in case the answer is negative, that means it'll be a compressive rather than a tensive one, as we have drawn here. Or it'll be, what it means, it'll be in the opposite direction to what we have assumed it to be. Then I have the summation of m dot v out. We have the unsteady term, which is 0. Then we have the m dot v out, so it's rho av times v2, right? Rho a2 v2 times v2, so that's why we have v2 square. And here we have v1 square. And we have found the a1, we have a1 and a2 and v1 and v2, and we have the pressure p. So now we want to find the pressure p1, and that's where our manometer comes in handy. So if you do a manometer, manometric, follow the pressures between 0.1 and 2 just through the manometer, so the pressure increases with depth, and then you take a constant height, because you're in the same liquid at a constant height, that pressure over here is equal to that, and then as you go up you subtract pressure of the mercury and then the pressure contribution due to the water, so you end up with pressure P1 minus P2. And P1 minus P2, with P2 being P atmospheric, is just the density difference between mercury and water times this G times H, this H. So plug that in with raw mercury 13,350, density of water is 1,000 kilogram per meter cubed, H is 58 centimeter, and with the velocities, V1 is 5 meter per second, V2 12.8, and with the area being pi over 4d squared, with D1 of 8 and D2 of 5 centimeter. When you plug all that in, you're going to end up with the bolt force of 163 newtons. So let's do one more problem here, and this is a similar case. You have a vertical bend, so that pipe is, this U-shaped pipe is 5 centimeters in diameter, and it's 180 degree vertical bend. They tell you that the length of the pipe is 75 centimeters, so that's typically along the center line. That's that length over here is between point A and point 1, and point 2 is 75 centimeters. And they tell you that the weight flow rate, that's a new concept, weight flow rate, but if you think about it, weight is mass times gravity, so that's a mass flow rate multiplied by gravity, so that's why it's called weight flow rate. So it's like mass flow rate times G is 230 Newton per second. They give you the pressure at section 1 and the pressure at section 2 to be 165 and 134. So these were probably measured with a device just like the manometer in the previous case. So this is a very similar problem to the previous one, so it's straightforward to do. Except now we have gravity pointing downward, so there's the weight of the liquid that's pointing downward. Again, we want our control volume, because we're after the force that the flanges or the bolts in the flanges have to withstand. We want to expose that force. Now we know what by having our control volume cutting, our control surface cutting through it, the boundaries of our control volume to be there. And you do it again, mass balance. Not really, you don't really, what mass balance tells you that because you have a constant diameter, that the velocity that comes in is the same velocity that leaves, and you can just compute the mass flow rate. And the mass flow rate, you get it from the weight flow rate, and it comes out to be 23.5 kilogram per second. And you also can get the velocity to be from the area and the density. So you get the velocity V1 and V2 is equal to V of 12 meter per second. So now looking at our control volume, it cuts through the flanges, and then we continue in atmospheric air, so we're not exposing any forces. So here we're only exposing the force in the flange, and also we're cutting through the water, so we're exposing the water pressure that's going through this through this control surface. And then let's do a sigma Fy. And what we have, sigma Fy is the rate of change of momentum. It's a steady problem, so this goes away. It's the mass momentum fluxes out minus momentum fluxes in. What external forces do we have? We have the weight of the control volume. So the control volume has everything inside it. It has air, it has water, and it has the pipe itself. But they tell you neglect the weight of the pipe. So we're going to neglect it, and we're only going to consider the weight of the liquid inside the pipe. And we can also safely neglect the weight of the air. It's just going to be negligible in comparison to the weight of the water. So that's what we mean by the weight of the control volume. So we have the weight of the control volume acting in the y direction. We have the pressure acting compressive and perpendicular, pressure times area, and then we have the flange force, F. So we have the flange bolt force acting. It's most obviously trying. So that's the force of the part that we have thrown away that's acting on our control volume. So you can see obviously it's trying to keep the two things together. If this F bolt weren't in the positive y direction, then the two things are going to come apart. The two pieces are going to come apart. So we're probably assuming the right direction, as in the previous case. Then we have the pressure forces P1A1 and P2A2, and you see they're both pointing towards the area. So they are, because the definition of pressure is compressive and perpendicular. So you want to keep that in mind. Any other forces? That's about it. So gravity is the weight, and then we have the momentum fluxes out and in. So let's plug that in. We have buoyancy in the positive y direction. P1 and P2 are in the negative y direction, so that's why we subtract them, as well as the weight of the control volume. We have momentum flux out, and so this is m dot v at the outlet. So this is V2, and V2 is in the positive y direction, so we kept it positive. And then we have a minus sign multiplied by m dot times V1, and you'll see that V1 is just minus v. It's in the negative y direction. So that's why we have m dot V2 minus V2, so that's 2m dot v. And the weight is just the length times the cross-sectional area of the pipe, of this curved pipe, 180-degree bend. It's their density times volume times gravity. We compute the volume as length times area and multiply by density of water and gravity. And when we plug all back into the bolt force, we're going to get a bolt force of around 764 newtons acting on my control volume. In the next example, so this is very similar to what we had before, except now we included the weight of the control volume. So in the next examples, we'll just go over them really quick. So here, what if we didn't have a 1D inlet or outlet? So far, what we have assumed in those two inlets, so in those two problems, whether in this case or in the previous flange problem, is that the velocity is uniformly distributed over the cross-sectional area of the pipe. So V1 is uniform of 12 meters per second here. So it's uniform over the area. And that's when it's uniform, it's average velocity. And here it's uniform of also 12 meters per second. So that's what we mean by 1D. What if we have a two-dimensional velocity distribution, that is, the velocity varies over the area, it's non-uniform? Then we have to, let's see what that effect what effect that has on our momentum flux. Remember, yeah, so we've done this mass conservation problem. So this is the mass flow rate going through this section. You really need to integrate, and you need to know what the velocity distribution over the radius r of this pipe of diameter 2r. And we're now interested in, so we're given that the velocity distribution to be parabolic, as in this case, and now we're interested in the momentum flux. This is the momentum flux. Rho times Vr dA, that's the mass flow rate multiplied by the velocity, that's the m dot v. And why don't you so I'm going to leave this example for you to exercise on and see what is the momentum flux that is going through this two-dimensional section, this section between these 2 points, this section of this pipe of radius r, and how does it compare to a one-dimensional, what is the equivalent one-dimensional momentum flux. So I will leave that to you. And if you look at the previous problem, we did that for mass flux, and we found out that the 1D equivalent velocity is actually the average velocity, which was the maximum velocity here, u0 max over 2. So I would like you to do that try an exercise on the momentum flux. Here it's done for the mass flux. Okay, momentum flux in the x direction. And now let's look at some other problems. So in this particular case, we're not going to solve it, we're just going to discuss it really quick. You have a container that is sitting on a scale, and the scale obviously is going to give you a reading of what weight you're going to get, but at the same time you have mass flux coming through from a vertical inlet, and it's leaving through a horizontal inlet. In this particular problem, they tell you that the mass fluxes at 1 and 2 are equal, so that makes the height and the volume of the water inside the container to remain constant. And the question that I have for you, will the scale read the weight of the liquid inside the container, or will it read something else? And in reality, this is a force balance. If you, let's just do a different color. If you try and do a force balance analysis of this problem, where you have this as your control volume, what you will notice is that this scale is acting on my container by providing a reaction force, which is W. This reaction force is the W reading that's over here. Let's call it R instead of W. So that there's a reaction force from the scale onto the container, but also we do have the weight of the container and the weight of the water. But you see, if you do have force balance, the summation of forces, let's call this the y direction. The summation of forces in the y direction is not just equal to the weight. Summation of forces in the y is just the unsteady term of the momentum inside the controlled volume. But since my level is constant, because the mass flow rate that comes in is the same mass flow rate that leaves, then this is a steady problem. So the unsteady term is 0 plus the summation of mass flux that leave m dot, and we're doing the m dot times Vy, m dot out times Vy at the outlet, and you'll see that your outlet is actually horizontal. There's no vertical component, so that's actually 0 minus the m dot times the mass flux, the velocity that that comes in. So m times Vn. And you'll see that Vn is actually a negative value because it's in the negative y direction. So we're picking all the velocities that are pointing upward to be positive, the velocities that are pointing down to be negative. So when you substitute for this, you want to substitute for Vn to be negative, while the R, the reaction, when you do the summation of forces, so here let's just write it down, you're going to get the reaction minus the weight, okay, so that's the weight here, so let's call this just mg, so that we don't get confused. That's mg. So let's just do that. Reaction minus mg, and mg includes the container and as well as the liquid inside, minus mg, because the reaction is in the positive y, the mg is in the negative y, is equal to minus, let's say we find the velocity to be 5 meters per second. So you're given the mass flow rate that's going through the pipe, you're given its diameter. So from the formula for mass flow rate, density, velocity, and area, you get a velocity. So let's say it's 5, just for argument, you get m dot, and you're going to substitute minus 5 because it's in the negative y direction. So keep that in mind when you're solving in this problem. And what you'll find out is that the reading of the scale is actually going to be 30% larger than the mg, or maybe 40% larger than the mg, primarily because there is momentum flux. What this reading, the scale reading, is giving you, it's giving you the effect of the gravitational pull, but also the effect of the momentum flux that comes in here. So this is actually one way, if you have, this is one way of actually measuring mass flow rate, because sometimes it's difficult to measure mass flow rate. If you can come up with this contraption to keep a constant level liquid by balancing the mass flow rate in and out to be exactly the same, so that that way you keep a constant height. When you do that, you can have predetermine what the weight is. You can read the reaction force, and you subtract the reaction force and the mass times g, and that will actually give you the mass flow rate that flows in through the pipe. So this is a methodology that's used in some hydraulic laboratories to compute or to measure the mass flow rate coming out of a pipe. Here is another example that I would like to discuss with you, which is a flying airplane. And if you see that you have an airplane that's cruising, which means cruising, it's keeping a constant altitude at 900 km per hour. It has engines that provide thrust force. So let's just change the color so you can see it. So it has two engines that provide thrust force of 330 kilonewton each, and it has a weight. So the engines are providing a thrust force, F thrust, each one is 330 kilonewton, and the airplane has a weight of 400 metric tons, so 400,000 kilograms times g, so that's m times g. And here's the question: what is the average shear stress acting on the body of the airplane, and what is the wing pressure difference? So this is actually a tricky question. What they give you is that they give you some dimensions about the fuselage, the wing area, and so on, cruising speed, and then they tell you the thrust and the weight. But this problem is just to show you the force balance that happens here. So this airplane is cruising, so that means it's not gaining altitude. It's not well. It's remaining at. It means it's at a constant altitude. They should say cruising at constant altitude. It's not going up. It's not coming down. So it's not accelerating neither in the horizontal direction, neither in the vertical direction. So it's in dynamic equilibrium in both directions, in the X and in the Y. So why is it in dynamic equilibrium? It's in dynamic equilibrium if I take the airplane as my control volume. It's all solid surface, so nothing is coming in, nothing is leaving, except for the engines, which I don't, at the moment, I wouldn't worry much about, because the net effect of that is the thrust. So in the horizontal direction, what you will, so we can simplify this problem, is that in the horizontal direction, the thrust is pushing you forward, F thrust, that's in the X, is being counteracted by what? By the friction force. That's the drag. And what is the drag force? It's pretty much, we're going to assume that it's just due to friction drag, the average shear stress. So it's tau times the area, the shear stress times the total area of the fuselage times the airplane. And which area? It's the area parallel to the velocity. So it's the external area. It's the pi d, or the W times H times L. If it were circular, it's the pi d times L. It's the surface area. So the drag is just the tau times area. How about that's the dynamic force balance in the horizontal direction. How about the vertical direction? In the vertical direction, you have mass times gravity. Mass is 400 tons, and in the vertical direction you get the lift force. What is causing the lift force? The lift force is nothing but the high pressure beneath the wing, and that's where the pressure difference across the wing. So beneath the wing you have high pressure, above the wing you have low pressure. So the F lift will be equal to the delta P of the wing times the area of the wing, So now this example is mainly to just explain to you this cruising flight force balance. All the fuel that you put in to generate thrust really goes to into friction, just goes to heat up the air around you. And the airplane is moving at constant speed. There's actually no work being done, because there's zero net force acting on the airplane, whether in the X or in the Y direction. There is no acceleration whatsoever on that body. But this is more it's not an example of momentum balance, but rather an example to tell you that the lift is related to the pressure across the wings, and the drag, or the thrust that's overcome by the thrust. The drag is the frictional shear multiplied by the parallel area. So this area is the area parallel to the velocity, and this is actually the area of the wing. So these are two different areas that we're talking about. So you want to be careful. This is the A surface, the A parallel to the velocity. Part of it will be, but here it's strictly the area of the wing. In this case, in the shear stress, it's the area of the wing plus the surface area of the fuselage. And in this case, actually, here it's area of the wing, here it's area of the wing times 2, because you have two sides, and the shear stress acts on the top side and on the bottom side. So it's twice the area of the wing plus the surface area of the fuselage over the whole airplane. So keep that in mind. Try and give it a shot, this example a shot. So there are actually more examples. I think to keep this it's become too long now. Let's keep it short at this length, and I will talk to you in the next lecture. Thank you.